today we're going to talk about section 10.7, which involves what's called Hess's Law. Okay, well, enthalpy we know is a state function, enthalpy being the energy or the heat transfer involved in a reaction. And so because it's a state function, it doesn't matter on the path taken to get there, it just matters on the initial and final conditions. And so because enthalpy is a state function, the change in H is going to be the same, H being enthalpy, whether a reaction between a specific reactant and product takes place in one step or a series of steps. So for example, let's look at, we've got nitrogen with plus O2 produces nitrogen dioxide, and we have a delta H value of 68 kilojoules. This is one way that we can react these chemicals together to produce this product. But that's not the only way. We can also break this up into two separate steps. So first we're reacting nitrogen with 1 mole of oxygen to produce nitrogen monoxide, and then we're taking that nitrogen monoxide and making it a reactant in step 2 plus oxygen to produce nitrogen dioxide. And so now we've got 2 steps instead of just the 1. But the interesting thing is, because enthalpy is a state function, no matter which step we do, we're going to get the same total answer. So delta H from the first way should equal the addition of the 2 steps from the second method. And this allows us to calculate heats of reaction that might be difficult to do in a calorimeter because we can't look at all the steps. And if we take the difference, 180 minus 112, because this is negative, we should get 68 kilojoules. Okay, also a quick reminder, because this is positive, that means that this reaction is endothermic. Same with this one. And then because this reaction is negative, that makes it exothermic. It's always good to be reminding yourself of those things. Okay, well, let's look at some characteristics of Hess's Law and these enthalpy changes. And there are some things you need to keep in mind. So if we reverse the reaction, if we take our reactants and make them products, and take our products and make them reactants, then that means the sign of delta H is also reversed. And so here we've got this reaction going this direction, producing XCF4. Now we've switched the direction. Now our products were our reactants. And if you can see, the delta H was negative for the first one, so this was an exothermic reaction. And now that we've switched, now that we've reversed it, this is positive, making it now endothermic. Okay, so when you are manipulating equations, and we'll do this in an example, make sure if you flip the equation, you change the sign. The other thing to consider is magnitude. The magnitude, or the value of delta H is directly proportional to the quantities or the amounts of the reactants and products. So if we multiply all those coefficients in the balanced chemical reaction, if we multiply them by an integer or any number, then the value of delta H is also multiplied by the same integer. So let's take, we've got xenon plus fluorine producing xenon tetrafluoride, okay, and we've got a negative 251 kilojoules for that. Now, if we go through and multiply everything through by 2, okay, and although this isn't the most simplified version, sometimes this is helpful when we're doing Hess's Law, then all we have to do is also multiply the delta H by 2. Okay, so it's kind of like math. Whatever you do to one side, you do to the other. Okay, so let's look at an example. So, given the following data, so we've got 2 reactions and their enthalpies. Calculate the delta H for this reaction. So the way that I kind of think about this is the answer that you're trying to get to. And these 2 are kind of like your variables, and you're trying to manipulate these to get this. And so you're not actually going to do anything with this one. You're just trying to manipulate those top 2 to get it to look like this one. So the first thing I would do is take a look at your first reactant. We have sulfur as a solid. Okay, take a look at both of these reactions. Hopefully you can see one that contains sulfur as a solid. Okay, it's this first one. And sulfur as a solid is also a reactant, which is where we want it in our answer. And there's one of them in our answer, and there's one of them in this equation. So we're not going to have to manipulate it at all. We're going to write it down as is. So sulfur as a solid, plus 3 halves O2. Now you're going to see some fractions as coefficients. For our purposes in Hess's Law, that's okay. Then goes to SO3 as a gas. And then I always write down the delta H's to keep track of them. So since we didn't change anything, I just write it down as normal. Okay, now let's look at O2. Both reactions contain O2, and so it's going to make it more difficult to manipulate. So I would leave the O2 until last, and it kind of works itself out. So don't look at things that are present in all the reactions. It makes it more difficult. So let's look at our product. We have sulfur dioxide. We've already used this first reaction, so we can't use it again. So now we're just down to this one. Well, here I've got one sulfur dioxide, and it's a product. If I look at this reaction, I have two sulfur dioxides, and it's a reactant. So if I want to get it as a product, I have to flip it. And then if I only want one of them, I also have to divide it by 2. And so I'm going to do both those steps at the same time. That means these are going to become my products, and this is going to become my reactant. So I'm going to start by writing this one and dividing it by 2. So I'm going to get SO3 goes 2. And I'm going to make these two my products, and I'm going to divide them both by 2. So 2 over 2 is 1, so I've got SO2 as a gas. Now there's 1 O2, and I need to divide it by 2. So 1/2 O2. Okay, now let's look at the delta H. I did two things to this equation. I flipped it, which means I changed the sign, so now it has to become positive. And I also divided it by 2. So I need to divide that value by 2. Okay, so my delta H is now positive, and I always write the plus so I know that I changed the sign and I don't have to question it. 198.2 over 2. Hey, we can calculate that right now, or you can plug it in at the end. I like to do it right now because then I know I don't have to worry about it later. And so that gives me 99.1. Okay, and so now I need to make sure that I've arranged these correctly to get my answer. So I'm going to cancel out things that are the same on both sides. I have one SO3 as a reactant. I have one SO3 as a product. Now let's look at the O2. I have 3/2 as a reactant, and I have 1/2 as a product. Well, I'm still, canceling them out the same way I did with these. Okay, this is the smaller one, and so it's going to totally cancel out. Okay, so that cancels. And then 1/2 minus 3/2 is 2/2. And so I should get S as a solid plus 2 over 2 is 1 O2. Okay, that's all my reactants. Goes to SO2 as a gas. And that does match my answer. Now let's look at my delta H. Okay, my delta H equals negative 395.2 kilojoules plus 99.1 kilojoules. So all I have to do is put those together. So negative 395.2 plus 99.1, and I get negative 296.1 kilojoules. Okay, so that's the delta H for that reaction, given those two steps. Okay, here is some practice to work on. We'll do a few more examples in class and then give you some time to ask questions. Have a good day.